Another concept that when we're looking at reciprocating devices, in this case a reciprocating engine, we'll draw this again and introduce the concept of mean effective pressure. So I'll draw this again. So we have the processes. I'm going to leave a little more room below this, like 1, 2, 3, 4, dB. And if you recall, this referred to, I had a piston cylinder here, and it went between down to here, and then it went back and forth. So if I look at this, this is called top dead center. This is called bottom dead center. And the difference between the two volumes is your piston displacement. So this is V sub PD, where V sub PD is your piston displacement. So if you have a car and it says the engine is a 2.5 liter car, that means the sum of the piston displacements of the swept volume that the pistons go through is 2.5 liters, or 5.2 liters if you have a Corvette. But it all depends on what your car is. And so, but this is the volume that goes through. It is not V3, it's this volume like this. And so that's your swept volume. So now what happened with the mean effective pressure, not to digress, is that this is the network. And what people did is they squished this network into a rectangle. So I'm going to let the network be equal to a rectangle, where the height is the mean effective pressure. So the mean effective pressure, P sub m, is equal to W net divided by the piston displacement. And so it's an artificial pressure. It has nothing to do with the real pressure. Obviously, the greater this pressure, the more work you get out of the greater this network is. So it becomes an easy way to say what the power intensity is, the work intensity of the engine is. And so to show you what a calculation might look like, let's say that W net is equal to 50 kilojoules, that V sub PD is equal to 10 liters, which is equal to 0.01 cubic meters. Remember, 1,000 liters is equal to 1 cubic meter. Then P sub m, W net over V sub PD, is equal to 50 kilonewton meters. A kilojoule is a kilonewton meter divided by 0.01 cubic meters. And the meter cancels here and we're left with 2. So this is equal to 5,000 kilonewtons per square meter, or kPa. So this gives us the kPa. Let's do another example, and we'll just see what this looks like. So we're going to have a Carnot engine, uses air, Qn is 53 kilojoules. The adiabatic expansion ratio is 16 to 1, and Tc is equal to 300 degrees K. So if I were to think about this, this entirety represents 53 kilojoules. Some of it, and I don't know what part, is going to be W net, and the rest is going to be Q out. And I want to find the thermal efficiency, W net, and Q out. So I want to find everything. What happens is that when I'm able to find the temperature, typically the problem becomes quite simple. So what I have here is that, let's see what we find out so far. I know Q in, and I know TC. So I'll draw this little diagram again, simply so that we have it in our mind. So I basically now I'm going to have that in my mind and be able to see what it is. And I know that the thermal efficiency is 1 minus TC over TH. But I know TC is 300. I don't know TH, and I don't know the thermal efficiency. So one equation and two unknowns is not good enough. So I now go back for algebraic problem solving, and I say, and I look to see what else I have here. And we say, well, this is W net over Q in, and I know Q in just as I know TC, but I still end up with the same number of unknowns. So, but what is the other piece of information I haven't used? The adiabatic expansion ratio. So I haven't, now what the dickens is the adiabatic expansion ratio? So what we look at is where is there an adiabatic process where expansion occurs? So the adiabatic process where expansion occurs is between 2 and 3. And what's happening there is the volume is increasing. The volume is increasing. So this adiabatic expansion ratio refers to the ratio of the volumes of V3 over V2. Is equal to 16. Now, and this is for adiabatic processes, or PV to the K, and I need to go back in chapter 6 and pay attention to the special case of the polytropic, the reversible adiabatic process, and we note that T2 over T3 is equal to V3 over V2 to the K minus 1, so this is equal to 16 to the 0.4, where K for air is 1.4. And so T2 is equal to 300 times 16 to the 0.4 is equal to 909 degrees K. So, and T2 is equal to, T2 is TC, so T1 to T2, it's all, T hot. It's all T hot from 1 to 2. So this is equal to TH. So now I have in this equation, I have TH, TC, I can find the thermal efficiency. Knowing the thermal efficiency in Qn, I can find W net. So the thermal efficiency, 1 minus 300 over 909 is 0.67, and 0.67 is equal to W net over 53. So W net is equal to 35.5, and Q out is equal to 17.5 kilojoules. So I have a Carnot engine. It receives 22 kilojoules of heat at 560 degrees K. It rejects heat at Q out at 270 degrees K. And I want to find, so it's producing work. I want the work in the mean effective pressure. And I'm given that V sub PD is equal to 0 0.127 cubic meters. So in this case, so if I look at this, I'm given these two temperatures and I want work and I'm given heat, that's pretty easy. So if I go over here, I'm given the two temperatures and the heat, and I want to find the work. So it's one equation with one unknown. It's embarrassing to have a problem that easy. And so what we look at is that the thermal efficiency is equal to 1 minus 270 over 560 is equal to 0.518. And so W net 0.518 times 22 is equal to 11.4 kilojoules. And the mean effective pressure is equal to W net over the piston displacement is equal to 11.4 kilonewton meters over 0.127 cubic meters. So the mean effective pressure is equal to 89.76 kPa. So it's a fairly easy calculation to do, and so that you have a little practice in doing some of these as well. Look at the following problems for homework. Seven point 1, 7.5, 7.9, 7.13. So when we look at these problems, anyway, these problems have you work your way around the cycle, so you have to go around the cycle, sometimes find cycle state points, and become familiar with how to use the Carnot cycle itself. So this is straightforward, and now in this case with the Carnot engine, we put heat in, we got work out, and we could use the work that we wanted to do. We could make it go in the opposite direction. We could put work in, and we could move heat from a low temperature to a high temperature. And we're going to say, why do you want to do that? In the first place is we want to keep cool. In the second place is we want to keep warm. And that's the basis of a refrigerator or a heat pump.